So really what I've covered then is a brief history of the digital twin. And now we're going to look at what is a digital twin and what is not a digital twin with some examples. So in terms of definitions, one of the, as I mentioned previously, I work with the Government Office of Science in the United Kingdom to pull together a definition of a digital twin, which is firmly grounded and based on NASA's definition. And I'm showing you this because there are three features within this definition that are really important. The first is that there is a collection of one or more computational representations. The second feature is that there's a flow of real-time data. The third feature is there's an ability to remotely interact with or control the physical asset. And that's really important. And all three of those need to be present for the system to be a digital twin. So definitions, now we're armed with this definition, we can filter out some of our imposters. And we can easily establish what I would say is one of the most common misrepresentations of a digital twin, and that is the digital shadow, which I mentioned previously. The digital shadow is shown here and has, yes, there's a physical system, there's also some data collection, and then that data is used and fed into the digital models that might run some simulations, etc., and predictions. But then there's a user in the loop. It's not a closed loop. The users or modelers will look at the results, and that may influence what they do and how they control the physical system, but it's not a closed loop. In contrast, the digital twin has the four elements. It has these three features: the real-time data, digital models, and ability to interact and control. And obviously there's a physical system and the four interfaces. So this is the digital twin, and all four interfaces and elements need to be present for it to be a digital twin. So now we've got our definition, we can look at some examples from industry. First example here is Porsche and their virtual design and prototyping platform. And really impressive, and there's a link here for you, I'm not going to show the video in this talk, but to go and have a look at this. And the question is this a digital twin? It's very, very impressive, and it has full dynamic simulation, drivetrain simulation, human-machine interface. But if we apply our definition to this, it is not a digital twin. Really impressive virtual prototyping platform, but it's not a digital twin. Second example is the case of a flood defense system. And here, weather and water levels are continuously monitored, and simulations are run based on the forecast or predicted incoming weather conditions. Those results are then used to control the flood defenses, things like sluice gates, etc. And this system is really model-in-the-loop automation and control. So is this a digital twin? The answer is yes. This satisfies our definition of a digital twin. And the H2 Porto system shown here was actually set up in about 2010 and has obviously evolved significantly, but is a good example of a digital twin, or it wasn't called that originally, that is in use and providing real value. But a couple more examples to look at, which are all digital twins. And perhaps it's rare we don't credit vendors or commend vendors enough, but Siemens have a very nice the way of classifying twins. They talk about product twins, performance twins, and production twins. And I've got an example of each of these that I'm going to talk about. So a product twin, this example is from Autodesk, working with the Bandito brothers. And what Autodesk did was to take the existing chassis, instrument that with hundreds of sensors, and then use the data that was collected to computationally redesign the chassis using their generative design tool. They then built another chassis, instrumented it, went out, raced it, and iterated that and repeated the cycle a number of times. And while the control, the ability to interact and control isn't instantaneous, they are taking that data, redesigning it, making it, testing it, redesigning it. So there is a closed loop there. Again, we've got a nice video link here if you want to go and have a look at that video in a TED talk from one of the Autodesk VPs. Second example is for Rolls-Royce engines, and I think a talk that covered digital twins or any aspect of health or condition monitoring wouldn't be complete without a nod or a mention of Rolls-Royce. Rolls-Royce began investing in their engine health monitoring in the 1990s, modeling the physics of their engines and collecting a large amount of operational data. Rolls-Royce now have around 14,000 engines in service, and the current generation, I think, as they talk about the three C's. So the first C is that engines are connected. They're connected with other engines, the support ecosystem, and with customers, allowing that regular two-way flow of information. And in addition to the core set of data that's recorded and exchanged, you can query an increasingly large set of other parameters in the engine. The second C is about being contextually aware, and that's contextually aware of the operating context, constraints, needs of the customer, allowing it to respond to environment around it. This is the engine without human intervention. So you can see again, that's the ability to control or interact, influence the physical system. The third C is comprehending, learning from its own experiences and from its network of peers to adjust its behaviour and achieve best performance. Think about the volcanic ash clouds recently, a few years ago. Aircraft on the same or similar flight paths, the engines would adjust automatically based on previous flights in the area, in the region or airspace, to try and maintain durability and performance. Okay, the example within the production environment, we've got actually 3 examples shown here on the right-hand side. We've got a full production environment, an automated production cell, and then a smart warehousing solution for DHL. And all of these twins really are built on the existing infrastructure, but are multi-physics based, multi-scale, so using things like discrete event simulation. And they're twins of the production system and production process. And the typical uses are for, I'd say, running what-if scenarios to enable improvements in quality management, process optimization, supply chain management, and aspects of condition monitoring and predictive maintenance. And they're being quite successfully used across a large number of production environments. So we've covered quite a lot in this section, and I wanted to conclude with some observations really around current digital twin applications. First, in particular, that many of the current digital twin applications are evolutions of, or based largely on extensions of, either established business processes and approaches, such as condition monitoring in the aerospace and defence sector, or they are using hardware and building on hardware capability infrastructure, such as in the production environment, where we've got SCADA systems, or they are extending the monitoring and control systems that are in place, such as those for critical assets or critical infrastructure systems, e.g. flooding or for bridges. And for a relatively small number, they may present a compelling cost-saving business case. One example would be NASA and the space missions, and the difference between a physical twin asset and keeping one of everything versus a digital. So what I'm really alluding to there is that the cost-saving aspect is not necessarily obvious, if you want, in all applications.